Just now, we are going to start our another presentation. Professor Paolino Caputo from University of Calabria, Italy. This presentation is going to be one of the NANOMACH conference pre-recording. The title is Ineffectiveness of a New Additive on the Chemical Structure of Etched Bitumen. Professor, do you hear me? Professor Paolino Caputo, do you hear me?
Morning. Yes, I listen.
Yes. Hello, good morning.
Good morning.
Welcome again. For the time, we are going to start your pre-recording about after 4 minutes later.
Perfect.
Okay.
I'm ready.
Okay. Hello again. Just now, we are going to start Professor Paolino Caputo's pre-recording. Professor, are you ready? Okay, and I would like to remind that this virtual congress is recording, and just now I am starting the Professor Paolino Caputo's presentation. The title is Effectiveness of a New Additive on the Chemical Structure of Etched Bitumen.
Okay, but sorry, I don't understand. I start my presentation or you start?
No, I am going to start because you sent us your presentation as a pre-recording. Just now I am starting, if you are ready.
Okay, perfect.
Good day to all. I am Paolino Caputo. I obtained my PhD in Life Science and Technology from the University of Calabria, Italy. I am currently a postdoc researcher in the Department of Chemistry and Chemical Technologies at the University of Calabria. My research focuses on physical chemistry with a main focus on bitumen characterization and food-based industrial materials and compounds. I currently have over 30 publications with over 270 citations. I am also one of the inventors of the anti-smoke for bitumen patent. To Today I will talk about the effectiveness of a new additive on the chemical structure of agent bitumen. What is the bitumen? Bitumen is a soft multi-components material that comes from the petroleum industry. For this reason, its chemical composition is complex and we can divide it into two big chemical families, asphaltene and maltene. Asphaltene are composed of highly polar amorphous solids with high molecular weight, while the maltene are composed of resins, oils, and waxes. This study aims to evaluating the different performance between a new green additive we call TPI and a softening agent we call soy oil, which both function as rejuvenating agents. Once removed and processed, the bituminous layers become reclaimed asphalt pavement wrap, which contains valuable asphalt binder and aggregates. In recent years, researchers have conducted many investigations on the use of wrap materials in the production of recycled asphalt. Oxidized bitumen is very hard because at high temperatures its aromatic components and resin, which are responsible for a certain grade of mobility, are oxidized to asphaltene and reduced to saturates. Additives can either have a rejuvenating effect or a fluxing effect. In general, the regenerating additive has chemically interacted with the oxidized part of the bitumen, restoring it almost totally to its initial state. A recurrent problem is the differentiation of a rejuvenating effect of an additive from a fluxing effect. At the moment, methods to distinguish a rejuvenating effect from a fluxing effect are not well defined. Hence, for this research work, we used several techniques in order to show a clear distinction between rejuvenating and the fluxing effect. We used dynamic shear rheometer, light microscopy, atomic force microscopy, infrared spectroscopy, and nuclear magnetic resonance. In order to study the effects of aging in the laboratory, the method known as rolling thin film oven test was adopted to simulate the aging of asphalt binders. The apparatus consists essentially of an internal double-wall furnace in which the hot air circulates conveyed by an internal fan at the test temperature of 163 degrees. The test consists in subjecting a thin layer of bitumen to a hot air jet for 225 minutes. Rheological measurements. To evaluate the effectiveness of rejuvenating agents, the rheological measurements were performed before and after aging process with or without additive. In general, after aging process, the viscosity property change and the transition temperature increase. A good additive restores the aged bitumen to value similar to the pristine bitumen before the aging process. To determine the rheological property and the transition temperature, rheological measurement has been done. In particular, the dynamic temperature ramp test at high temperature 25 degrees up to 100 degrees and at low temperature 25 degrees to minus 30 degrees at the rate of 1 degree per minute at the frequency of 1 Hz were performed on all samples. In this picture we show semi-log plot of temperature ramp test at high temperature for all samples. At high temperatures the transition temperature is evidenced when tan delta is plotted against the temperature up until the point where it's no longer visible on the plot. We observed that the transition temperature increased with the aging process. Both additives decrease the transition temperature of the bitumen, and they both have a similar rheological profile. However, with this analysis, we were unable to distinguish the rejuvenating effect from the fluxing effect. In this picture, we show a semilog plot of temperature ramp test at low temperature for all samples. Phase angle value at low temperature are quite scattered, owing to instrumental problems related to the high material consistency and therefore to the low measured deformation. In this case, we observed that both additives have similar rheological behavior to the pristine bitumen, while the edged bitumen is very hard in comparison to them. Those in this case also confirmed the rheological result at high temperature, and we were unable to distinguish the rejuvenating effect from the fluxing effect. Light microscopy. In the next slide, we show the light microscopy analysis of the asphaltenic fraction of the bitumen. The asphaltene of the unaged bitumen begin to melt around 150 degrees and are completely liquid at 160 degrees. Those of aged bitumen, being oxidized, begin to melt at high temperatures, in particular around 165 degrees, and are completely liquid at 180 degrees. The asphaltene derived from the sample added with 4% TPI begin to melt at 155 degrees and are completely liquid at 170 degrees, showing a behavior very similar to those derived from non-aged bitumen. While the asphaltene derived from aged bitumen added with 4% soy oil instead show values similar to those recorded for asphaltene of aged pristine bitumen, 160 degrees, 180 degrees. In this case, it is possible to observe a significant difference between the asphaltene derived from the samples of aged bitumen modified with soy oil and TPI. Thus, we can say that the regenerating additive TPI has chemically interacted with the asphaltenic part of the bitumen, restoring it most totally to its initial state, while soy oil, having simply improved the flow of the aged bitumen and therefore not having chemically interacted with the bitumen, shows a behavior very similar to aged bitumen. Atomic force microscopy has been proven to be a useful technique which gives consistent, meaningful results in the study of the bitumen at the macroscopy level. In bitumen FM images, 4 different phases which are often said to correspond to bitumen fraction are identifiable. They are katana phase, big structures, periphase, paraphase, and cell phase. In the next slide, we show the phase and the topography images of the pristine and aged bitumen samples with and without 4% additives. In the pristine bitumen and aged bitumen samples, the domain sites are similar. the interconnection of the domains appears to be greater in the case of the aged bitumen sample than in the depressed bitumen sample. In the soy oil and the TPI samples, the domains are much larger, and in the case of the TPI, they seem to be less connected than in the soy oil case. In the phase figures, it is observed that the soft part of the sample, dark part, is higher in pristine bitumen than in aged bitumen, where the clear part, hard zone, prevails. This is due to the oxidation of the bitumen during the aging process. In the images relating to the samples with the addition of the regenerating additive TPI, an increase in the soft hair is observed, and these images are very similar to those obtained for non-aged bitumen. Samples with soy oil instead show very similar images to those recorded for aged bitumen. This effect is more evident in 3D figures. We can therefore say that even this technique allows us to distinguish the regenerating effect from the fluxing effect. Infrared spectroscopy is a well-known, reliable method for investigation of the chemical changes in bitumens due to aging. Amongst the technique used for analyzing bitumen, this technique is consistent and reliable because it tells unambiguously distinguishing different groups of molecules bound at different wavelengths of an absorbance or transmittance spectrum. In infrared spectrum, frequencies of light which are absorbed by molecules due to their matching with the frequencies of the natural vibration of the molecular bonds appears as peak. The first thing to observe is that the yellow spectra relating to non-aged bitumen are almost overlapping to those obtained for aged bitumen plus 4% TPI, as well as those obtained for aged bitumen are very similar to those obtained with aged bitumen plus 4% soy oil. Analyzing in depth, we observe how the peak relative to the stretching of aromatic compounds in aged bitumen is drastically reduced. In the sample with the TPI additive, this peak grows until it reaches values similar to the initial pristine bitumen, which does not happen in the sample containing soy oil. The opposite behavior is observed for the typical peak of the sulfide functional group, where we have higher intensity peaks for the aged and the aged plus oil, and medium small peaks for the non-aged and aged bitumens added with TPI. This confirms once again that the additive chemical reacts with the bitumen, regenerating the oxidized molecules. An advanced molecular investigation was conducted using NMR in order to analyze the chemical aging process and microstructural modification. The Fourier transform NMR self-diffusion coefficient allows insight into the bitumen microstructure by detecting the long-range mobility of the mixture constituents. It is crucial to note that the self-diffusion coefficient value of asphaltene molecules cannot be detected owing to the short transverse reactions time of their protons. So, hereafter, the measured self-diffusion coefficient value are related to the melting phase. The observation of self-diffusion is based on the mobility of molecules. The motion of these molecules can be hindered due to the observation they face during their mobility in media. The typical data observed where the motion occurs can be considered as a fingerprint of the microstructural behavior. These results are very interesting, but they need a deeper outlook due to the fact that the results obtained were not in line with the expected results. In conclusion, the TPI additive is an excellent rejuvenating agent to bitumen. The radiological measurements were indicative, but they didn't provide enough information to distinguish between a rejuvenating effect and a fluxing effect. Light microscopy, infrared spectroscopy, and atomic force microscopy provide useful information to evaluate the rejuvenating effect of the additives. Nuclear magnetic resonance results are promising, but future major investigation work is needed to obtain a useful relatable scientific meaning. Thank you for your attention.
Thank you, Professor Caputo, for your nice presentation.
Thank you.
And now I want to ask to all of our participants, do you have any questions to Professor Caputo about his presentation? If you have any question, you can write your questions to chat part, or if you want to ask your questions by yourself, please write about you have a question to chat part, and we can open your system's voice and you can ask your questions by yourself. Also, we can wait a few minutes if there's any question or not. I think there's no question for now. Thank you, Professor, again for your nice presentation.
Thank you.
And now we are going to have a coffee break about 10 minutes. 10 minutes later, we are going to be here, and our virtual congress is going on.